Okay, continuation of chapter 6, and so today we're going to talk about periodic trends. So this is when you're going to need the periodic table that I have for you that has arrows on it. And so we talked a little bit about a trend at the end of the last video. So on your periodic table, on the arrow going down, so let's go ahead and write that metallic properties increase. So that just simply means that potassium is more metallic than lithium. Francium is the most metallic. Okay, so as you go down this family, the electrons are easier and easier to remove. And so if a property increases going down, it's going to do the opposite going across on the very top arrow. Let's write metallic properties decrease. Okay? Okay, so let's talk about atomic radius. So atomic radius, so since atoms do not have clearly defined outer limits, they have an electron cloud, their size is measured indirectly. For metals, such as sodium, potassium, whatever, the atomic radius is defined as half the distance between adjacent nuclei in a crystal of that element. So you can go to your ebook and it's going to show you an example of that. For elements that occur as molecules, such as O2, N2, H2, the atomic radius is half the distance between the nuclei of identical atoms that are chemically bonded together. So for atomic radius, trends within a group or a family, so keep in mind that a family and a group are the same thing. Atomic radius will generally increase as you move down the family or group because, so here's your reasons why. Number one, you have increasing main energy levels. So you're adding, so every time you move down the family, you have one more energy level. So this hydrogen would have 1, lithium would have 2 energy levels, sodium would have 3, potassium would have 4, okay? As you add energy levels, the electrons are getting further from the nucleus, so it offsets the pull of the increasing nuclear charge. There's also something called shielding. So if you're talking rubidium, so rubidium's outer electron is shielded by all the electrons in these other energy levels. So you have shielding effect with each additional main energy level. Additional orbitals between the nucleus and the outer electron are occupied, thus shielding the outer electron from the pull of the nucleus, from the protons in the nucleus. Trends within a period. So in general, there's a gradual decrease in the atomic radius as you move from left to right across a period because there is an increase in positive charge in the nucleus. So each time you add a new element as you go across, there's one more proton in the nucleus. And the fact that the electrons are added to the same energy level. There is no shielding effect. So anytime you go across a period, you never have shielding. And the result is that the increase in nuclear charge will pull the outermost electrons closer to the nucleus. And so in your book in chapter 6, there should be a table that shows you examples of this. Okay? So now we're going to, on the second arrow going down, we're going to say atomic radius increases. And going across, we're going to say atomic radius decreases. Okay, so far we have two things going down. So both metallic properties and atomic radius both increase as you go down a family or group. So it simply means that cesium would have a larger atomic radius than potassium. So we have a couple of examples. So put this on pause and then let's go over what you circled. Okay, the first one says circle the element with larger atomic radius. So you have carbon, you have fluorine, you have beryllium, and you have lithium, these are all in the same family. Excuse me, they're all in the same period. And the one with the larger atomic radius, remember radius decreases going across, so the one with the larger would be lithium. So you should have circled lithium. The next example, circle the one with the larger atomic radius. So now you have magnesium, you have silicon, you have sulfur, you have sodium. So once again, they're in the same period. So remember, as you go across a period, your atomic radius will decrease. So the one with the largest would be sodium. And the one with the smallest would be the furthest one over, so that would be sulfur. And then we have one more example, which has the largest radius, helium, xenon, argon. So these are your noble gases. So you know that your family or group, your atomic radius increases as you go down. So the one further down would be xenon. So it would have the largest atomic radius. Okay? So that is atomic radius. Now, atoms often will give up or gain electrons and become ions, especially if you're talking about a metal and a nonmetal interacting. And so an ion is an atom that has lost or gained electrons. Cations are positively charged because they have lost electrons. So they're either going to lose 1, 2, or 3 electrons, depending on which family they're from. So we get a 1 plus 2 plus or 3 plus charge. They will always be smaller than their parent because, number one, you have lost electrons from the outer level, so you will leave it empty, so they will have a smaller radius, plus the fact that the positive charge of the nucleus remains the same, so you have more positives than you do negatives, and the nucleus will pull those electrons in closer. So, for instance, if you had lithium, and it got rid of its outer shell electrons, so now it only has 2 electrons, but it has 3 protons, so there's more positive charges, so it pulls those electrons in tighter. Anions are the other type of ion. They are negatively charged because they have gained electrons. They will always be larger in size than their parent because, number one, you have added electrons, and so these electrons start repelling other electrons in that level, causing them to spread out. Okay, so your family trends and your period trends. So ionic radius for both cations and anions increases as you go down a family. In a period, going from left to right, there is a gradual decrease in size of cations. Then beginning with group 5A, because starting with 5A, they're picking up electrons, so those are your anions. They start out larger in size, but then they gradually decrease as you move from left to right. Okay, so your table, so the third arrow going down, put ionic radius increases. And then going across, notice that we have 2 sets of arrows. So we're going to put a, so this first set goes with your guys that are going to lose electrons, so they're going to be positive. So put a positive here and a positive here. And so you're going to say cation radius decreases. And then starting at family 5, these are going to gain electrons, so they're going to become negative. But they'll start out larger since they're picking them up. So you're going to say anion radius decreases. Didn't leave you much room there, did I? Okay. Okay, so ionization energy is our next topic. It is defined as the energy required to remove an electron from an atom to form a positive ion. Think of ionization energy as an indication of how strongly an atom's nucleus will hold on to its valence or outer shell electrons. A high ionization energy indicates the atom has a strong hold on its electrons and are not likely to lose them to form a positive ion. Low ionization energies indicate an atom loses its outer electron easily to form a positive ion. Now, there are different ionizations. So we have what we call first ionization energy, second ionization, and third ionization energy. So first ionization energy is the energy needed to remove the first electron. Now, if you remove a first electron, now you're going to have a +1 cation. So the second ionization energy is the energy needed to remove the second electron from a positively charged ion. And then if you want to remove a third one, and you already have an ion with a 2+ charge, so it is the energy needed to remove the third electron from a 2+ ion. The energy required for each successive ionization always increases, however, not by equal amounts. For each element, there's an ionization for which the required energy jumps dramatically, which shows atoms hold on to their inner core electrons more strongly than their valence. So we're going to look at a table here in a second, but this family has one valence electron, so they'll give it up relatively easily. But if they want to remove a second electron, the next shell in is full, and that's why we take so much more energy. This family has two valence electrons, so they get rid of one, takes a little bit more energy for the second. If they remove the second, or when they remove the second, if they want to remove a third, then their third electron is in the inner shell that is full. And then the same for 3A. Okay, for group 1A metals, which are hydrogen, lithium, sodium, etc., there is a large increase in energy between the first and second ionization energy. It's easy to remove the first electron from this group because their outer shell contains only one electron, but it is very difficult to remove additional electrons. For group 2A, the large increase in ionization energy occurs after the second electron is removed. And for group 3A, the large increase occurs after the third electron is removed. Okay, so let's look at this table. It's on an overhead, so I'll put it on a white sheet and hopefully you can see it. Just go on here in a second. Okay, so if you find hydrogen, lithium, sodium, so these all have one electron, potassium. Okay, so it would take, for lithium for instance, it takes 520 kilojoules per mole to remove one electron. For sodium, it takes a little less, 495.8. And for potassium, it takes 418. The reason it's decreasing, we'll talk about this in a second, is those electrons are further from the nucleus, they're easier to remove. But if you want to remove its first one, it takes this amount of energy, but if you want to remove its second one, it takes way more energy, over 7,000 kilojoules, okay? Because that second electron would be from an inner level that is full. For sodium, same thing. After the first electron, it takes so much. For the second, it would take a great deal more energy. If we find beryllium has two valence electrons. It's in 2A, along with magnesium and calcium. So for beryllium, it takes 900 kilojoules to remove the first one. It's going to take a little bit more for the second one because you've gotten rid of one, so the nucleus is pulling on a little bit tighter. Now, it has two electrons in its outer shell, so if you want to remove a third one, the third one is from a shell that is full, and so there's going to be a big jump there, okay? Okay, so here are your trends. Ionization energy generally decreases as you move down a group or family because as the size of the atom increases, valence electrons are further from the nucleus, making them easier to remove. Trends within a period, and this is for your representative elements. Across a period, there is a gradual or general increase in first ionization energy as you move from left to right because the nucleus is holding onto the electrons more tightly. You can make a general statement. In general, nonmetals will have a higher ionization energy than metals because nonmetals don't want to get rid of electrons, they want to pick up electrons. Okay, so you've got a couple of example problems. So you can put this on hold for a minute and answer them. Okay, the question says circle the element in each pair that has the larger ionization energy. So let's go ahead and write on our table. So our fourth arrow down, we're going to say first ionization energy. Oops, I forgot ionization. Stick ionization in there. First ionization energy decreases going down, because remember those electrons are further and further from the nucleus. And then going across the period, we're going to say first ionization energy increases, because remember, as you go across, you're going to hit your nonmetals, and they don't want to get rid of electrons, they want to gain them. Okay. So who has the larger ionization energy? Sodium and potassium. They're in the same family, and so ionization energy decreases as you go down. So the one with the larger, you should have circled sodium. Okay. Magnesium and phosphorus. Magnesium, phosphorus, they're in the same period. Ionization energy increases as you go across, and so the question says who has the larger, and you should have circled phosphorus. Okay, last topic is something called electronegativity. Now, I think hopefully on the periodic table that I printed off for you, or you should have one already printed off, that has a table on the front, and on the back side it has the names of some polyatomic ions, and it has at the top another little table that has little numbers written off, okay? Oh, it's going to look kind of like this. All right. Okay. So electronegativity, or EN. So we'll come back to EN when we get into the chapter on bonding. Electronegativity is defined as how strongly one atom attracts the electrons of another atom when they are combined in a compound. The EN values are expressed in terms of a numerical value of 4.0 or less. Now, this is not going to be very clear, but you can see, for instance, that hydrogen has a 2.1, oxygen has a 3.5, fluorine has been assigned a value of 4.0. This table was developed by Linus Pauling. When we talk about bonding in a couple of chapters from now, in a chemical bond, the atom with the greater EN value will more strongly attract the bond's electrons. So those electrons are going to be pulled closer to it. Group trends. Within a group, so as you look across, when you look down a group, so here you have 2.1, 1.0, 0.9, electronegativity will decrease or have similar values, because larger and more easily ionized atoms will attract electrons less strongly than smaller, less easily ionized atoms. Your alkali, which are your 1A, and your alkaline earth, which are 2A metals, are the least electronegative. They do not attract electrons in a compound. They're trying to get rid of them. Nitrogen, oxygen, halogen, those are your nonmetals. They're the more electronegative. They want to gain electrons to fill their outer shell. Okay, periodic trends. Across a period, there's a gradual increase in electronegativity. Nonmetals are generally more electronegative than metals because they want electrons to fill their outer shell. And then you can make a general statement. The lowest EN values are found in the lower left corner. So down here, cesium will have the lowest, while the higher EN values are found in the upper right-hand corner, with fluorine having the highest. So there's kind of a diagonal trend also. Noble gases are typically not assigned a value because they already have 8 electrons in their outer shell, so they have an octet. Okay, so you have a couple of problems. If you want to put me on pause. Okay. Now, before we answer those, let's go ahead and write on our table so we don't forget to do this. So we're going to say EN values for electronegativity decrease, going down. A family or group, and therefore your EN values will increase going across. Okay, circle the one with the higher EN value. So you have sodium and rubidium, they're in the same family. Your EN values decrease going down, so you're wanting the greater, so you should have circled sodium. Oxygen or fluorine, well, fluorine's the most electronegative, so circle fluorine. Cesium or sulfur, there's that diagonal trend. It increases as you go diagonally across, so you should have circled sulfur. Okay. For metals, as a general rule, as you move down the family, they become more metallic. We've already written that on our table. And they become more reactive. Group 1A are the most reactive, with cesium being more reactive than potassium. They want to give up their outer electrons. Group 2A are not quite as reactive as 1A. And keep in mind that the most reactive nonmetals are located at the top of 7A. So that finishes up the notes for Chapter 6. Now you will complete your set 2 periodic trends. Thank you.